Hi, I'm Josh Robinson with Beckman Coulter Life Science. I'm a senior application scientist here. I'm here to introduce the latest and greatest technology from Beckman Coulter particle characterization. This is the DelsaMax line of instruments, the DelsaMax Pro and DelsaMax Assist. Now, this state-of-the-art technology is able to give you the best analysis for your nanoparticles and proteins. It's able to simultaneously get the size and stability through dynamic light scattering and zeta potential. It's very easy to load your samples in and get a result out in just a few minutes. There's two main ways for loading, so we'll go over those now. Now, before we get to loading our sample, we first need to focus on the flow cell, which is where all the action takes place. The flow cell is located at the top of the DelsaMax Pro instrument. The sample flows in from the left side, where it's interrogated by a laser, and then it'll flow out through the right side. At any given time, there's 170 microliters of sample in the flow cell, which is roughly 2 or 3 drops worth. This is all the sample that's needed to be able to get an accurate measurement of both the size and stability of your nanoparticles or proteins. Now we've covered the flow cell, we can get to the two main loading options for the DelsaMax Pro. All right, now I'm going to introduce how to properly load a sample into the DelsaMax Assist. First thing we want to check is to make sure both the DelsaMax Pro and DelsaMax Assist are on just by using the power buttons in the lower right side. Looking at the main screen, I see that my laser is on. I monitor this with the laser power. It's around 50 milliwatts. That's the power you'll want to have it at to know that it's properly warmed up. I generally suggest around 30 minutes of warm-up time before you start your experiment. I have a sample here in a 1 ml syringe. This is the generally accepted way to load the DelsaMax Assist is with 1 ml syringes. We loaded 50 nanometer latex particles in seltzer water or carbonated water. Very, very bubbly, very difficult to run in your traditional nanoparticle characterization instruments. To load, we see the injection ports right in the center of the DelsaMax Assist. So we'll just snugly insert our syringe. We want to make sure that the sample is okay to load. So there's color-coded lights on the bottom of the DelsaMax Assist. When the blue light is on for load, that indicates that it's okay to load your sample. If the orange pressurized light is on, that means that both the inlet and outlet valves to the flow cell are closed off and you're not able to load your sample at that time. We have the blue light though, so that says go. We inject our sample slowly. And we inject in roughly 500 microliters. On the main touchscreen, we see a quick jump in the red graph. This corresponds to the forward monitor amplitude. This lets you know how much signal is actually getting through to the detector. Ideally, we want to see this around above 1 volt up to 2 volts. But right now we're at 0 volts because of all the bubbles in the seltzer water and the carbonated water are forming inside the flow cell, and they're just scattering the light. They're making sure that no light actually gets through to the detector. So that's the advantage of the DelsaMax Assist. We go to the Assist tab on here, and what we can do is pressurize the flow cell. And by pressurizing the flow cell, we're going to eliminate all those bubbles we introduced while injecting it into the system. The pressurized button is in the lower right-hand side. We turn it on. This graph monitors the amount of pressure that's going into the system. So we've pressurized our flow cell now with the DelsaMax Assist from its starting pressure, which was roughly 1 bar, or the same pressure as the Earth's atmosphere, up to 8.72 bar, which we're able to monitor on this graph, as well as get a quantified reading at the bottom. This is 8 times the pressure of the Earth's atmosphere. It's pressure is equivalent to what a diver will experience when they're diving to the bottom of the ocean. At this higher pressure, the bubbles actually dissolve back into the water. At higher pressure, gas has higher solubility, so all the bubbles that are evolving out of the seltzer water, out of the carbonated water, are now redissolving back into the water, and they're being eliminated from the flow cell. We're able to monitor this by going back to the main screen, and we see that the forward monitor amplitude has jumped up to 2 volts, which indicates nearly 100% of the light is getting from the flow cell into the detector. The final step is to look at the DLS tab. This gives us the autocorrelation function, which is the main output from a light scattering experiment. This smooth sigmoidal curve is what is used to determine the hydrodynamic radius of the nanoparticles or proteins. You see it starts high, slopes down gently, and then reaches a flat line. That slope actually indicates the size of the nanoparticles. And a smooth line is what you want. When you have bubbles or dust or smudges on your flow cell, you'll see a very jagged line. You're not going to see it smooth at all. It's going to kind of go all over the place. When we depressurize the assist, this is actually what we will see on the autocorrelation function, is that it will begin to jump around a little bit. And you'll begin to see just the start of some noise here in the lower right-hand corner. But this time, go back, repressurize the assist. We've once again eliminated the bubbles that reformed the second we depressurized it. We see we once again have a smooth DLX function, and we're now ready to start our experiment and begin the analysis in the software.